All right. Good afternoon. Sorry that it took long again since it doesn't like my laptop. So let's start our first lecture. The first thing I already posted the lecture file on Canvas. We'll start with critical section. It's very important concept, and we will see. You are going to use this entire of this semester for this course. Suppose we have a beam as one mechanical component. Beam, columns, or other mechanical components can be an example for this. So this beam is under some loading. Some concentrated loaded and distributed loaded is applied to this beam. So if the failure occurs in this beam, if this beam has a failure, it's going to happen in one section. One of the sections in this beam is going to fail, and it's going to break at that section. Suppose this is the where that we have break, or it's going to fail at that section. We call this section as a critical section. So as definition, critical section is the location in design where we have the largest load internal load is developed and the failure is most likely. So this is the definition of critical section. When you are given with a mechanical component like this is the beam, you depends on the problem, you are either going to design or analysis. Design means if the length of the beam is given, you are sizing the cross section. Suppose if you have a square in cross section, you are sizing the thick or the thickness of this beam such that it's not going to fail. This is the design. And what is the analysis? If T is given, suppose 1.5 centimeter, and the length and other thing is given, you are answering this question if we have failure or not. So either way, what we are going to do first, we are going to find the critical section, and then we are going to do the design for that critical section, or if we are supposed to do the analysis, we are doing the analysis for that section. So this is why finding the critical section is important, because the either analysis or design is starting from that point. So what do we know about the critical section? It's not known at the beginning. If I give you this beam, you cannot find, you don't know where is the critical section by just looking at this. So the first thing that you need to find, locate the critical section. You should find where it's gonna be the critical section. To locate that, we should consider the external load applied to mechanical component. So whatever is our mechanical component, either beam, shaft, or column, we should consider the external load. By considering the external load, we can find the location of critical section. How we can do that, we will work on this next week, hopefully. But these are the steps that you need to do. After you locate the critical section, we determine the load applied to the critical section. So suppose this is the location of critical section, you will find your determine the loads applied to that critical section. The load is going to be the forces. How can we find the forces? Drawing free body diagram. And using static force equilibrium and moments, static moment equilibrium equation. So in this course we don't have any motion on the component. So the beam is not moving. So we have a static, we can apply the static equilibrium equation. For the force, for two-dimensional, if we have two-dimensional problems, so suppose we just can move in this plane. So we are gonna have two forces. Force either applied in x direction, and summation should be equal to 0, and force along y direction, it should be 0. It's a force equilibrium. And moment equilibrium in two-dimensional plane, it can rotate about z-axis, which is coming out of the plane. Sigma mz equals to 0. So 3 equations for two-dimensional. So for three-dimensional, you can guess 3 forces, Fx, Fy. It's the mass general situation, and moment can happen about all 3 axes. My, Mx, and Mz can happen. So you have 6 equations for 3-dimensional. Either way, either 2-dimensional or 3-dimensional, we are going to use this equation. First, we are going to do the free body diagram and applying this equation to find the forces. For beams, you can use the shear force diagram and the bending moment diagram to find the shear force and the bending moment applied in the critical sections. So after you figure out the forces, you go to the stress. You can calculate the stress because you know what would be the force. Now it's time to calculate the stress applied to the critical section. Then, after you calculate the stress, you apply the Mohr circle to finish the analysis. You may remember that by using the Mohr circle, we are going to find the principal normal stresses. We will go through them, but just.
Would you mind doing a short review of the Mohr circle when we get to it?
Sure. So we are going to have. We are going to go over that completely. It's not a short review. I'm just saying the steps that we are gonna do on our analysis in this course. So the rest of semester it's just for different problems or different components, but the steps would be the same. I'll bring it here. We just continue. We just review this for different components. So these are the steps that we should do when we want to do design or if we want to do the analysis for a mechanical component. So again, the critical section is very important concept. Yes.
What is SFE and
Bending moment diagram and shear force diagrams. These are for beams. We will go through that as well.
Thank you.
Shear force means the vertical force applied to the beam, and the bending moment is the moment applied to the beam over the entire of the beam. So let's start with the stress. Any question before we move on? So let me just have a quick review on this. When you are given with a design problem or analysis problem of a mechanical component like beam, column, shaft, fasteners, or power screw, first of all, you need to find the critical section. By looking at the component, you don't know where is the critical section, but by considering the external loads applied to the mechanical component, you can figure out where is the critical section. After you figure out the location of critical section, you determine the loads applied to that critical section. So the loads, I mean the forces, moments, first. How can you find that? The force and load by drawing the free body diagram at the critical section and using this equation. If you have two-dimensional problem, we are using this equilibrium equation. If you have three-dimensional, we have 6 equations. If you have beam, we can draw the shear force diagram and the bending moment diagram to find force and the moment applied to the beam. After you find the force and moments, you can calculate the stress. After you find stress, you apply the Morse circles to find principal normal stress. And then you can answer the question if the failure occurs or if you want to design, you can finish your design and size the dimension of the mechanical component. Suppose there is a bar with the length of A here and 1 right here. A and 1. Consider 1 point right here, somewhere here, point A, at the middle of this bar. How many planes can I pass through this point? Just infinite. I can cross this plane, or I can cross this plane, or I can cross this plane. Infinite plane can go through these points. So the definition of the stress is force. Suppose it's under axial load of P. Stress is P dividing by A. But it's an incomplete expression if I say stress at point A is P divided by A, unless I specify which plane point A is lies in it. So if the plane is this, so you can then define the stress. But before you go to the definition of the stress, you should specify which plane you are talking about. So by changing the plane, stress at point A is gonna be different. I didn't change the load, I didn't change the size, I just changed the plane. So by changing the plane, I'm gonna get a different stress. So, and it's because definition of the stress, because force divided by the area. So the area is coming from the plane that you define here for passing through point A. So this is one important thing that you should know. Suppose in this case, I would like to have this plane. So if I look from the top, I will see something like this. And point A is going to be at the middle. So associated with this plane, we can have three terms of stress. Associated with this plane that I passed through point A, I can define three terms of stress. Two stress is going to be the tangent to the plane. We call them shear stress. So tau 1, tau 2, I will talk about this later shortly. And one term is normal or perpendicular to the plane. We call it normal stress. Again, we started with the stress at the point. We learned that due to the definition of the stress, we should specify which plane we are talking about, and we have infinite plane passing through point A, so we can have infinite stress terms defined, but at the specific plane that I have here, I can define three terms of the stress. Two stresses are tangent to the plane, and one term of the stress is normal or perpendicular to the plane. The tangential stresses are called shear stress. Normal stress is normal or perpendicular to the plane and designated by sigma. So we label the normal stresses by sigma. And tangential stresses are tangent to the plane and designated by tau or shear stress. We call them shear stress. If normal stress acting outward on the surface is called tensile stress. I said we have one normal stress which is perpendicular to the plane. If the normal stress is acting outward of the plane, which is coming out of the plane, we call it tensile stress. Look at this. This force is applying in this direction, so the stress, the normal stress applying to this plane is coming out of the plane. It's coming out of the plane, it's a tensile stress. But the normal stress acting anywhere on the surface is called compressive. If it goes into the plane, it's going to be the compressive. If I change the force direction, it's coming into the plane. So it's going to be compressive. Now, just want to show you, if I change the force from this direction to this direction, force P applying in this direction here, and another force applying here. So on this plane, you are going to see the tangential stress, which is going to be perpendicular, tangent to the plane. You are going to see this one. If I apply in this direction and this direction, you are going to see the other tangential stress. In US units, the unit of stress is pound PSI, pound per square inch. And in SI, the unit of the stress is Newton per meter. Newton per square meter. And 1 Newton per meter square is going to be 1 Pascal. Pascal is another term for the stress. Any question so far? Seems just start working. All right, we are talking about the stress for at any point, like point A. In general, at any point, like point A, there are three mutually perpendicular planes passing through. So at any point like point A that I have here, you can imagine that we can pass three mutually plane passing through that. Just look at the one point on the corner or right up there. This plane, this wall, the other wall, and the floor is passing through that point, and they are perpendicular to each other. So what I'm gonna do, I'm gonna represent the stress, the state of stress at point A, or at any point. Point A is a general point. So if this is axis X, axis Y, and axis Z, and the origin is point A. For point A, I just pass this plane, and the floor. These three planes. And just to close that, I assume one cube here with six faces. So this is what we call is a state of stress for point A. So point A, the state of stress for point A is gonna look like a cube. How many faces or how many planes do we have? 6. One here, another one on the other side. One below, another plane up there, and one right here, and one back there. So 6 planes. Associated with each plane, we have 3 terms of stresses. 2 tangential and 1 normal stress. I will start with this plane. This plane. This plane has the axis of x normal to that or perpendicular to that plane. So I will call this plane X because the axis of x is perpendicular to that. If I want to show the normal stress to that, I should use the term of sigma, and the subscript that I use for that is gonna be the axis of the plane. What is the axis of this plane? It's x. So right here for this plane, if I want to represent the normal stress, it's gonna be sigma. What is the axis of this plane? This plane has the axis of y, so I use the subscript of y for this one. And for this plane, the axis of z is perpendicular to this plane, so the axis of that is z, so I will label that as a sigma z. For right here, for this plane right here, which is in the opposite side of x plane, I can define sigma x in the other direction, but just to save the space, I don't show the arrows over there or in this plane or on the back of this cube. So I'm just showing the arrows in this plane, right here, and this plane. Now it's time to represent the shear stresses, the two tangential stresses. On this plane, I can have one shear stress in this direction, tau, and another one in this direction, another tau. How can I label them? The first subscript is gonna show the direction of the plane. The plane is plane x, so I use tau x. Tau x. For shear, I'm gonna use another second subscript. What would be the direction of this shear stress is going in y direction. So I use y after the x. And what would be the direction of the other shear stress is gonna be in z direction. I use tau xz. So I'm done with this plane. I have 1, 2, 3 terms of the stress, one normal, two tangential. So I move to the second plane. Second plane, I already have the normal. For the tangential, I'm gonna have this and this. Two tangential stresses. This is gonna be tau because the shear stress. The first subscript is y. This shear stress is in x direction. I label this as x, second terms. And this one is going to be tau y. But second one is going to be in z direction. It's in z direction. It's going to be tau yz. Done with this one. For this plane, which is the last plane, this shear stress is going to get the subscript of z, and second one is x. This one is going to get tau z. It's going in y direction, tau zy. So now I'm done with the state of stress for a general point like A. So how many terms of the stress do we have? Sigma x, sigma y, sigma z, tau xy, tau x z, tau yx, tau yz, and these two, tau zx and tau zy. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 terms are the so these 9 terms, they define the stress elements for point A. It's a general case. I mean, many of them it's going to be 0, but they can show up if depending on the loading. So I draw this state of stress over there, but it's gonna be the same. 3 plane, 1, 2, 3. You can show the other 3 plane, but I just want to save the space. So I just showed these 3 planes, but we know that we have 3 more planes. In each plane, we have 3 terms of the stresses. As I said, 1 normal, 2 tangential, 1 normal, 2 tangential, 1 normal, 2 tangential, and last plane. How can we label them? This plane has the axis of x, which is perpendicular to that. So whatever is the axis of that plane, label the normal stress with that. Sigma x, sigma z, and sigma y. For the shear, the first subscript is going to be the axis of the plane. If it's x, use the x. If it's z, use the z. And if it's y, use the y. And second subscript is going to be the direction of the shear stress. It goes in x direction, use x. It goes in y direction, it changes to the y. And the total terms of the stress is going to be 9. So next thing that we can talk about that on the state of stress, many cross shear stress terms are equal to each other. What do I mean by cross shear? I mean, if we have tau xy, the cross shear is yx. Tau xy is this guy. It's on plane x in y direction. Tau yx is on plane y in x direction. So we can prove that tau xy it's going to be equal to tau yx, and tau xz is going to be equal to tau zx, and tau yz equal to tau zy. I just switch the subscripts, so they are the same. These two are the same, these are equal to each other, and these two are equal to each other. So 9 terms will change to 6 terms. Sigma x, sigma y, sigma z, tau xy, tau xz, tau yz. Now, let's do the first class activity. If we have a general state of stress for a point A, but we know that all stresses in plane Z are 0. So, if all stress elements in plane Z are 0, draw the state of stress for this case. Is that clear what I'm asking? No? This is a general case for the state of stress for a point. Now, I'm saying that all stress terms in one plane, I said plane Z, are 0. So whatever terms that you can see in this plane, just consider that as 0 and just draw the cube again. Is it better?
So you want a picture?
Yes, something like this.
Basically only lists the variables that will have an actual value associated.
Yes, exactly. Just remove the terms that you don't see on that cube. Number 40. Where are you? Okay. Yep.
I don't know.
Just if you want to draw this cube again, what I need to do, I just need to remove sigma z, tau zx, and tau zy, because I said all stresses in plane z are 0. So I don't see anything here. I see sigma x, sigma y. Here I have tau xz in this plane. But since tau zx equals to 0, this one also is going to be 0. So I don't have this one. I only have tau xy here. Similarly here, we only have tau yx here. We don't have tau yzy because tau zy is going to be 0. So now if you look from this cube, from this side, from front side, you will see one cube like this. Sigma x is going this side, tau xy is going up, tau yx is going this direction, and sigma y is going up. If I look from front side. So we call this plane stress. Why plane stress? Because all stress element in one plane would be 0.